Today's topic of discussion is auxiliary memory. What do you mean by auxiliary? Auxiliary means secondary. In the earlier days, or we can say, um, 2 decades ago, the auxiliary memory was magnetic tapes, magnetic drums, magnetic bubble memory, optical discs. Until recently, we used to have CD-ROMs, DVDs, and all. But nowadays, auxiliary memory has been totally replaced by cloud. You store all the information in your cloud and in your USB flash. But then it is in the syllabus, we have to study this. So different types of auxiliary memory are magnetic disks or hard disk, magnetic tapes, uh, and magnetic drums, bubble memory, optical discs. Optical discs include CD drives and DVD drives. They are uh, having huge capacity to store the data, and the price is low compared to main memory and cache memory. And we'll look at magnetic disks. Magnetic disks is a circular plate. It can be constructed of metal or plastic with a magnetized material. What happens is, like this, you have spherical shaped discs. They are known as magnetic discs. These are called as tracks. On magnetic disc you have tracks, and you may have multiple magnetic discs, and you may have a spindle. This is known as a spindle, read write head spindle. On this you can have another magnetic discs, and there is a read write head. This is called as a read write head. This is like a hard disk. In this you have these magnetic plates. They are divided into concentric circles called as tracks. These are called as tracks, and each track is divided into smaller units known as sectors. This is a sector, and all the concentric circles um, at at one location is known as cylinder. Cylinders. This is read write head. Okay, this is our hard disk. What happens is, sometimes you may use both the sides of the disk for recording the information or storing the information, or you may use only one side. And all the disks rotate together at the same speed, and bits are stored in the magnetized surface in spots. Means here you have spots where you can store the bits. These are magnetic spots. Okay, one important uh, point to remember here is, Access time. Access time to get the information from the disk to the processor is known as the access time. Access time is made up of seek time and transfer time. Seek time is required to position the read write head to a location. What happens is, suppose if you want to read this data, you have to read this data in this sector. Then what you have to do? First you have to move this disk and bring the disk under this read write head, and then move the read write head to start reading the desired block of information. So that moving of this read write head is known as the seek time, and the transfer time is to after you get the appropriate data, the desired data under this read write head, you have to start transferring it. The time taken to transfer the data is known as transfer time. Access time is equal to access time is equal to seek time plus transfer time. Hope that this concept is clear. Magnetic disks and okay, here also it is given like this is a disk, this is read write head, these are tracks, and this is a sector. You also have magnetic tapes. Magnetic tape is also magnetic material strip. uh, Magnetic disc is a circular shaped metal or plastic material, whereas magnetic tape is a strip made up of plastic coated magnetic recording material. The primary difference, okay, did you look at the cassette? If you have looked at a cassette, earlier days you had a tape recorder and a cassette. To play the music, you used to put the cassette in the tape recorder, and then you used to play the music by rewind or forward because it was sequential. Directly you cannot jump to a particular song and play it. So magnetic tapes are like that. Those tape recorders, no, cassettes. Those cassettes. They can't play the data randomly. Rather, you have to uh, read or write sequentially. That is magnetic tape. These two comes under secondary or auxiliary memory. Now we have so many. We have USB flash. This book has been written long ago, so this is the prescribed thing, you are reading it. Associative memory. Okay, this is a very important concept. Associative memory is also called as content addressable memory. Let us look at this, how it works. This is eraser. new board. Content addressable memory. Okay. You know, primary memory, we studied RAM and ROM. They are chips. So let us consider RAM, random access memory. This RAM has locations and the address, each location will have an address 0 to 2 to the power of n minus 1. 2 to the power of n minus 1. What is given to RAM? If you want to read data stored in the RAM, what is given? Address is given. You specify the address. This is our content. In this location, content is stored. The input is address, output is content or the data stored at the address. This is our RAM, random access memory. If n is 7, how many locations you will have? 0 to 2 to the power of 7 minus 1, which is equal to 127. So these are addresses. These are addresses. What will be stored in this? Data and instruction may be stored. At 0th location, if you have a data 10. So if I give input as 0, what will be the output? 10. Suppose at location number 10, A is stored. If I give input as 10, what is the output? A. Whatever is stored. Essentially, random access memory takes in the address and gives out the content stored at that address. That is RAM. Now let us look at associative memory, which is also called as content addressable memory, CAM. In CAM, there are no addresses. You don't have any address mechanism in this. You have the data stored in these locations, and if you have to search for a data, you have to specify either the entire data block stored or the part of the data block. Suppose this is stored, this contains one data element. Okay, this is one data element. In order to get this data element out of this is CAM, this is RAM, this is CAM, content addressable memory. So what you have to specify as input? Either you have to specify the entire data element or the part of the data element. You can specify only this part and can get the data element, or you can specify the whole of this. And what is the significant feature of CAM is it is super fast. extremely fast, and it performs search in parallel. So for search critical applications, you have to use CAM. When you specify, for instance, 101 as the data that is to be searched in this, what happens is, in parallel, if there are 3 bits stored, so this one is compared concurrently at the same time with all these bits. This 0 is compared with all these bits. This one is compared with all these bits. And then you have here a memory map. This memory map uh, will get a value 1 when it matches. When this data is matched with the content stored at this location, and matching can happen for more than one data element also. It's not always necessary to match only with a single value. All right. So what happens here is, for instance, this is 101. This is also 101. Simultaneously, 101 is searched at all these bit locations, bit positions. Then this memory map will get 1 here and 1 at the last position. Why? To indicate that this word and this word, these 2 words got matched with this pattern which has come as input, and therefore this word and that word both will be sent out as output. This is content addressable memory. Okay, let us look at the hardware. This is the memory which stores the words. This is memory map, which is match register. Here I showed you this is match register. This is the memory. Associative memory, array and logic. Argument register is the one which holds the input, which is to be searched across this associative memory words. Uh, in the example which we discussed had 101. So argument memory will have 101, and then key register is a mask to denote whether you are searching for the entire word or the part of the word. If key register contains all ones, and here you have a sequence of bits, essentially that means you are searching for all the bits present at argument register. Subsequently, this argument register content is matched with all this at the same time, because key register had 1 in its entire word. In case key register has ones only for specific positions, only those positions in the corresponding positions of the ones in key register, uh, and the argument register, they are considered to be matched here. Let us look at an example. A is argument register, which is having a value 101 and 4 ones and 2 zeros. K is the mask, which is having 3 ones followed by many zeros. What does that mean here? It means we are trying to search only for 101, not for this entire word. This part of the word you are trying to search. Why so? Because the corresponding bits of 101 are 111 in K, whereas the corresponding bits of this entire segment is having 0 at K, and therefore only these 3 bits will be matched against the words in the associative memory. These 2 are the words in the associative memory. This 101, this 100. There is no match. This 101 and this is 101, there is a match. Look at this associative memory structure in terms of bits. There are n bits in argument register. There are n bits in key register, as well as there are n words. The size of each word, not n words, the size of each word is n, and there are m words in memory. There are m words. The size of each word is n, and there are m match positions. Whatever data stored in argument register, if it has corresponding ones in key register, that is compared in parallel at the same time with all these 3 bits. This bit A1 is compared with C11, CI1 and CM1, this bit 1 at once, so it's very fast. AJ is compared with all the 3, and AN is compared with all the 3. If these 3 matches with these 3, this M1 is set to 1. If they don't match, it is remained to be 0. And when that is possible? Only when key, mask is having a value 1. The match logic is, what happens if A and F both are 1 1 or both are 0 0, only then it gets matched. F can be this, F can be this, F can be this. The bits in the words, if both matches, means if A is 1 and F is also 1, you get 1 here. If you get 1, then x of x sub j is 1. X sub j is what? This can be x sub j. This can be x sub j plus 1, x sub j plus 2, like that. When do you get 1 here? When this A is having 1, and consider this to be F. F is having 1, A is having 1. When both are 1 1, or when both are 0 0. If both are 0 0 also, you get xj to be 1. xj, okay, what happens is xj is only for a one particular bit. When m is said to be 1, when all x's, actually I said x this way, but x is that way. Consider x to be horizontally. So this is xj, xj plus 1, xj plus 2. When m1 will be 1, when xj is 1, xj plus 1 is 1, xj plus 2 is 1. When all x's are 1s, then this is said to be 1. Is it clear? This is the match logic. You get a, you get k, and you get the whatever value is stored. If k is 1 and a and f is nothing but the c value, both matches, then m is said to be 1. And you can read in and you can perform write operation also by using AND operation. Key k. If k is 1, you get x value. If k is 0, the bit k sub j bit, we are talking about the bit position. If k sub j means the first bit or the second bit is equal to 1, then uh, then xj, you take the value of xj, whatever is the value of x. If kj is 0, then the value will be equal to 1. Why like that? Because if k value, if k is the corresponding position of this one is having 1, so this one and this one will be compared, a and c1 or w1. When k is 0, these two are not compared, so by default it is equal to 1. That's why when k is 0, kjth bit is 0, by default you get 1. Otherwise, if kjth bit is 1, in that case you have to check whether the bit in A and the bit in C matches. If both matches, you get 1. If they both don't match, you get 0. So m value is set. This whole exercise we are doing to set the value of m, which is the match position, match position of ith bit. So if you want to set the match position to be 1, what should happen? This x1, x2, x3 and xn should be equal to 1. When all are matching and k1, k2, these should be equal to, or this should be equal to 0. When they are equal to 0, you are making them to be 1 by using not. Uh, you have any doubt, you can stop me and ask. The whole idea here is, if you just understand that content addressable memory will take as input the content value and not the address, because it does not have any address. It takes the content value and then it maintains two registers. This is our memory. Besides this memory, we also have two other registers, which are argument register and key register. An argument register holds the content or the data that is to be matched with the contents of CAM. Key register is the mask that specify what part of argument register has to be matched, has to be compared. And then you also have another register called as match register. In this match register, what happens is when the argument, contents of argument and the contents of CAM gets matched, match register will get a value 1. To do all that, to do this, what we are doing is we are trying to uh, computationally, mathematically, we are expressing how to do all that. So M will be set to 1. This is whatever is the M value. It can be 1 or it can be 0 also. It can be x1 plus, this is plus means or, x1 or you can go for this k1 dash. Why it is k1 dash? If it is, this is, here it is. When kj is equals to 1, we have kj dash is equal to 0 and xj plus 0 is equals to xj. If you put 0 in this position, from the rules we know that x plus 0 is x. When kj is equals to 0, then xj dash is equal to 1 and x plus 1 is equal to 1. Look at here, we are getting 1 here because kj is 0. 0 when kj is 0, this literal will give 1 and x plus 1 is equals to 1. When kj is equals to 1, you are here negating it. This literal will give you a value 1 and 1 this literal will give a value 0 because kj is 1. This will give 0. 0 plus x is x. This. I hope it is clear. And then this expression can be written in this form, like this is a product of aj and fij. Fij is nothing but that c value. Instead of using c, you are just using f. Ij is ith word and jth bit of c. And this is when both are 1 1, you get 1. When both are 0 0 also you get 1. Or when kj is equal to uh, you know 0. When kj is equals to 0, you are negating it and you are getting 1 here. So this mi is nothing but the product of all this. Okay, how is read operation done? Same thing. This is the match logic. No, this figure corresponds to the match logic. Mi, how do you get mi? A, this is a n, it too, this is and an and f ij, you can say. This AND operation is a n dash and fij dash. These two are corresponding to that equation. this equation. This equation. Xj is equals to Aj Fij plus Aj dash Fij dash. And then you also have to add to this. This is Xj plus Kj. So here you get Kj. Kj should be negated. So this negation. And everything is summed up. And whatever is the result, that is the value for M. Like that you do for every bit position. Okay, so read is what happens in read is, if more than one word in memory matches the unmasked argument field, all the matched words will have 1 in the corresponding bit position of the match register. Okay, match register will contain ones, and you read that content. Write is randomly, you can write anywhere. Uh, yeah, write what happens in RAM to write. To write in RAM, to write, what you do is you have to specify two things to write in RAM. You have to specify the address. Because these every location has an address. So essentially what you do is you give the input as data plus address. Data will be stored. Suppose if you give a comma 1, means at first position you want to store 1. So here at 1 you store a. This is RAM, because address and data both required. In to perform write operation on CAM, you don't have any address. To record which positions are free and which positions are occupied, you may use a tag register, in which you just put value 1 if it is free, if it is not occupied. So what you can do, whenever A has to be written, if you get an input A to be written in the content addressable memory CAM or associative memory, you check in the tag whichever location you find first which is free, you just store A in that location. You don't have any address. That is write operation. Any doubts, students? Tomorrow we'll look at cache memory. Do you have any doubts in associative memory or content addressable memory?
No, ma'am.
Sure, you understood?
Yes, ma'am.
Saraswati and Nandini. Okay, then please go through it. If you
Okay.
get any doubt, tomorrow you can ask. Bye.